In software engineering, we are discussing chapter number 23, testing conventional applications. Equivalence partitioning. Though it is a test case design philosophy, before we go ahead, let us understand what is this equivalence. Any relation, that is, a set, is equivalence relation if it is reflexive, every element is related to itself. If it is symmetric, every relation A to B is also B to A. Transitive, if A is related to B, B is related to C, then A is related to C. So these kind of relations are called equivalence relation. That is, the values are equivalent. They are regarded as equivalent. Now, if we just divide them or take the subset of this equivalence relation, what do we get? We get the equivalence class. So, equivalence class, subset of equivalence relation, and all the elements are equivalent. So, equivalence partitioning is a black box testing method that divides the input domain of a program into classes of data, from which the test cases can be derived. The important part is, an ideal test case single-handedly uncovers a class of errors. For example, incorrect processing of all character data, like that. So if you take any of these in this set, equivalence class, any value, for that you may not have to make many test cases. Only one element of the equivalent class can uncover all class of the error, or single-handedly. So it has come from equivalence classes, and I told you what is equivalence relation, what are equivalent classes, and if equivalence relation, reflexive, symmetric, transitive is there. Before we go ahead with the example, let me tell you the equivalence class will represent the valid or invalid states for the input conditions. Input conditions or value can be either a specific numeric value, it can be a range of values, it can be set of related values, that is a set, or it can be a Boolean condition, true, false, yes, no, right, wrong. So we have certain guidelines. So equivalence classes, how to make them? See, for every one what we have to do, each of them. First one is, if the input condition, the condition is a range, then one valid and two invalid equivalence classes we need to define. If the input condition requires a specific numeric value or a specific value, one valid and two invalid equivalence classes are defined. If an input condition specifies a member of a set or related values, now here we will have one valid and one invalid equivalence classes. If the input is Boolean condition, one valid and one invalid classes will be defined. Okay? So how do we do this? Let us take an example here. And let us take the OTP example first. One-time password. So normally it is 6-digit, and we are also saying that it is 6-digit. So how do we equivalence partition it? We get this OTP in our mobile messages and emails. So this is a specific value, okay? But it is defined that it has to be 6-digit. So we can have valid values, that is 6 digits has to be there, these are the valid. And since it is a specific numeric value or set of related value, you can argue like that. But the main thing is, I've shown you the invalid, that is 4 digits or 7 digits. If it is not 6-digit, then it is invalid. 6-digit, it is valid. So either you can make one valid and two invalid, or one valid or one invalid. These are the classes. That is, we will take one value which is invalid, one value which is valid. 6 digit is valid. Anything other than 6 digit, that is the 7 digit or 4 digit, 3 digit, 8 digit, so you can make invalid class and valid class. Okay. Now coming to the other example, for example 6 to 10 is valid. So 0 to 5 can be invalid and 11 to 14 is also invalid. This is how we take the equivalence partition in class. And the important part is we will combine the binary value analysis BVA with this, and that will create a more promising test case. So this is the equivalence partitioning test case design. How many valid and invalid test cases we have to make? Valid and invalid, both are test cases. Boundary value analysis. Now when you are traveling, you don't have map. Assume you don't have map. So if you're going straight, you don't have to ask anyone. But whenever you have multiple turns or a cross intersection, then you have to read the board. Here you have the problem. Similarly, most of the time, in the coding, the boundary values create problem. So boundary value analysis is one of the widely used test case design technique for black box testing. This is used to test boundary values because the input values near the boundary, they have higher chances, higher probability of error. So we'll make the partition, valid partition, etc. But error occurs more at the boundaries of the input domain rather than the center. So boundary value analysis leads to a selection of test cases that will exercise the bounding values or boundary values. So this boundary value analysis, it is complementing the equivalence partitioning. Once you have made the equivalence partition, say for example 2 invalid class and 1 valid class you have made, you see the examples also is given. And how do we do the boundary value analysis? In these 3 equivalence classes, we will take these boundary values and then apply the test cases. So boundary value analysis leads to selection of test cases at the edges of this class, equivalence class, if you apply equivalence class partitioning. So boundary value analysis, not only for the input domain, you can derive test cases for the output domain also. This is very important. For example, if you have divided this whole range into valid and invalid classes, for example, equivalence partitioning you have done, then the actual boundary value analysis will be done at 18 and 30. That is a value which is near 18 and near 30. The 28, 30, 31 and 17, 18, 20. These are the values which are of your concern while applying the boundary value analysis. These are the value I am making circle. Sometimes people say that the boundary value analysis, if we compare with the equivalence partitioning, though they are complementing each other, but BVA is considered more better because it may take the positive and negative values both along with the minimum and maximum value. So what are the guidelines for BVA? How do you actually do it? So the guidelines or the way you are going to do it is, if an input condition specifies a range bounded by say values A and B, say A is 10, B is 100. So test cases should be designed with values A and B which are just above and below both A and B. For example, 10 you will take 9 and 11 also, 100 you will take 99 and 101 also. If an input condition specifies a number of values, if you have number of values, then what you will do? You will take the minimum and maximum numbers and then you will use the test case for minimum and maximum. And then the minimum which is the value which is just above and below minimum, and above and below the maximum. And this too also can be done to the output condition. For example, if you have a temperature versus pressure table, this is required as output for say certain engineering analysis program. Then how do we apply boundary value analysis to this output condition? The test cases should be designed to create an output report that produces the maximum and minimum allowable number of table entries. If you want a table, what will be the maximum allowable values? What are the minimum allowable values? This has to be done. This has to be your test cases. This is for the output condition. If the internal program data structure, they have prescribed boundaries. For example, we are taking array, defining an array. Now if this array is 100, you have defined. So you know array starts with 0 and with 99. Most of the time the error comes at 100. If you want to access any number which is higher than the array being defined, there will be an error. So you have to check it at 98, 99, 100 and in between also some value. So a table has a defined limit of 100 entries, right? So be certain to design a test case to exercise the data boundary at the boundary. Now these are the valid and input say classification we have done, equivalence classes we have made. And then what you have to do is you have to take the values which are at the boundary of these classes. Negative, positive. That is how boundary value analysis works. Orthogonal array testing, OAT. Now what is an array? Simple array. It is two dimension. That is, you define an array like this. It is a contiguous settlement of memory elements. You can access any value here with some array with subscript. Okay. Now orthogonal array testing, when we have multiple dimensions, we need to have the orthogonal way of understanding. So orthogonal array testing is a software testing technique that uses orthogonal arrays to create test cases. This is all about minimizing the test cases. I'll tell you when the cases will be very high and how we can boil down to the low test cases. It is a statistical testing approach specially used when system to be tested has huge data inputs. So this orthogonal array testing helps to maximize the test coverage by pairing and combining the inputs and testing the system with comparatively less number of test cases for time saving. For example, 100 is there, you just need 10 of them. How is OAT represented? The formula is like this. So L, see, this is 2 dimension and I am talking about multiple dimension. For example, third dimension can be added like this. So you have to understand the orthogonality like this. Like the AX, Y, Z axis, then one more element, one more element like this. So we represent it by L, then runs, levels, and to the power we write factors. What are these? Runs, levels, factors. See, first of all, the runs, these are the number of rows in the array which translate into number of test cases that will be generated. Okay. Factors will be number of columns in the array which translate into maximum number of variables that can be handled. And levels will be maximum number of values that can be taken on any single factor. Okay, these are just definition, but we need to understand with an example. So let us take an example. This is an example web page. Just assume we have 3 distinct sections and these sections can be anytime hidden and can be shown. They may be visible, they may not be visible. So the first one, we say that this is the top part, top. The middle one is middle The lower one is bottom. So a web page that has 3 distinct sections that can be individually shown or hidden from a user. Now let us see how do we make the formula and what all these represent. L, and whatever we write here, we'll write here. I'll tell you how do we get it. But first it is the power, that is, what is number of factors? Factors is 3. Top, middle, bottom. These are number of factors. Now the levels are hidden and shown. Every top can be hidden and shown. Middle can be hidden and shown state. And the bottom can also be hidden and shown state. So the level is 2. Factor is 3. 1, 2, 3 factors. And 2 is the level. And this 4 has come from where? This 4 has come from a table. Okay. This table I am showing you on the far right. So where was the factor? Where was the levels? It is 2 raised power 3. Level raised power factor. And here was the 4 array type. So from 4, where has come? From where we deduce 4? See, most of the time people say 2 to the power 3 n equals 4. These are the combination. So for multidimensionality, if it is 2 raised 3, you will get 4 L4 matrix, this L4 the orthogonal. Then we have, if it would have been say 2 raised power 4 or 3 raised power 4, n would be 9, so it would have been L9 3 raised power 4. Okay, I hope you got the idea. 2 is what, 3 is what? 3 is the number of variables. L is the variable states, or a variable can take how many states, and this 4 or 9 has come, that is from this table. Now how many test cases can be generated? 2 raised to the power 3. Sometimes people say, let us make it more easier, 2 into 3, 6 test cases. Most of the time it has to be 8, because this is the logical understanding. But even if we don't want to understand like that, 2 into 3 is 6. 6 test cases are there. Our main idea is to reduce the test cases. These are the simple test cases. Top can be hidden and shown. So test 1, test 2 correspond to it. Bottom can be hidden and shown. Either hidden or shown. Test 3, test 4. Middle can be either hidden or shown. It can be test 5, test 6. So 6 test cases are being designed. So how does this orthogonal array testing reduces the test cases? This is the conventional way of doing it. Orthogonal array testing will give you only 4 test cases. These are the test cases. And on the matrix, you can assume it to be a table. Top, middle, bottom, these are the 3 variables. Variable 1, variable 2, variable 2. Every variable can take 2 values, hidden or visible, and these are the combination of the variable values. For test 1, let me just give you an example. Let me make it more easier. If we say the hidden is 0 and visible is 1. So the test case number 1 will be the top value will be hidden, the middle part will be hidden, and bottom value will be hidden. So if you make a orthogonal array, you can easily pinpoint 0, 0, 0, or the test case 2, hidden is 0, visible, 1, 1. Now this particular point can also be shown on an orthogonal array. So this 6 has changed to 4 just by using an orthogonal array. Okay. This is the use of orthogonal array testing. In this orthogonal array testing, as the number of input value grows, you can say number of variables, and each variable takes different discrete value. That is, each data item, different values can be taken. There are immensely number of test cases that can be made. For example, A can take 0, 1, 2, B can take say 0, 1, 2, C can take value as 0, 1, 2. Now if ABC is okay, if you go up to Z, for the larger products or projects, it will be various variables, various input values. A can go up to 3, B can go up to 5, C. So exhaustive testing is not possible. Here we apply the orthogonal array testing, and this is applied when input domain is small but too large to accommodate the exhaustive testing. So OAT is useful in finding the region fault. That is, if A is 0, B is 1 and say C is 2, then the problem is coming. So this is the faulty logic. At this point, the logic is faulty. Let us take 3 input values, for example, 3 input items X, Y, Z. Now this X, Y, Z, so 3 values, and they may take, each of them can take 3 values. So how many possible test cases are there? 3 to the power 3, 27. Now this is manageable. Okay. What is the geometric view of the possible test cases? Here you have X, Y and Z represented with the X, Y, Z axis. And these round points are the possible test cases. If one item at a time, if we assume that the result is relatively limited coverage of the input domain, if we equally distribute it, one item at a time, if we distribute it using the L9 orthogonal array, or here you see, when OAT occurs, an L9 orthogonal array of test cases is created. So the L9 orthogonal array has a balancing property, and these test cases are represented by dark dot. In order to understand this, because this was just the theory, let us say we have a send function for some faxing application. 4 parameters are there: P1, P2, P3, P4. Or you can say 4 variables are there, and the function is send. So this is a function send. We have 4 variables: P1, P2, P3, P4. And each of these, that is P1, can take, say, certain values, 3 values. P1 can be 1. It can be 1, corresponding to send it now. P1 can be 2, send the fax 1 hour later. Or P1 can be 3, send it after midnight. So if one item at a time we take, that is just a simple way of representing it. P1, P2, P3, P4 combination. Now if you see all these combination, only one value is changed. Here it is 3, here it is 2. Only one value is changed because we are taking the policy of one input item at a time. And that will create immense pressure on the test cases. But these would only uncover only single mode faults. If any one of these has error, the faults can be computed. And what are the number of test cases required? 3 raised to the power 4. Okay, 3 raised to the power 4, which is 81. 4 variables are there, and each variable can take 3 options. 81. But when we go ahead with various numbers, we have a problem. So Fadke, he actually introduced it. Actually, this is called a Taguchi design. So Fadke assesses that we can have it solved by L9 orthogonal array testing. That is, if we have send P1, P2, P3, P4, a single mode fault is consistent problem with any level of any single parameter. If P equals 1 causes an error condition, it will be single mode failure. Okay. Now, the 1 and P1 and P2, we have to choose that also. That is called the double mode faults. If only P1 or P2 or P3, P4 is giving some error, it is single mode. P1, P2, double mode. Combination of all these is multi-mode faults. So what we do here is, we make a Taguchi design. And only 9 test cases we can make. Only 9 test cases. And this is a prescribed way of doing it. I am saying that this is 111, 222, 333 for P1. 123, 123, 123 for P2. P3 is 123 and then becomes 231 and 312. P4 becomes 123, 312 and 231. This is you have to write. And now test case 1 will be P1, P2, P3, P4 for all these values. Okay, this is all about this discussion. Thank you so much.